All right, welcome back. So we're looking at finding limits algebraically today. So we're going to use more algebraic processes to find these values and limits. So these will be functions that are either we don't want to waste time graphing or too complicated to graph or whatever's going on. So the idea is very straightforward. As we kind of discussed with the graphs, to evaluate the limit and the value of the function are roughly the same thing at most locations. The only times they are not the same is the idea of having a hole in the graph, which we've talked about with rational functions. Vertical asymptote, which we didn't see with these graph limits, but would obviously cause an issue because there's nothing there at that spot if there's a vertical asymptote. Or really gaps in the function due to a piecewise function. Everything else, though, is typically going to have a value. So, and it's always going to equal the value at that location. So to do them algebraically, we just substitute that value in and just see what we get. So here for A, we have the negative cube root of 2x minus 4. So if we did the negative cube root of 2 times 1 minus 4, negative cube root of 2 minus 4, negative cube root of negative 2, if it was a square root negative inside, it would cause imaginary, cause issues. Cube roots or odd roots in general, we don't care. In fact, we just pull the negative out, and it cancels the negative on the outside. So the limit as x approaches 1 of negative cube root of 2x minus 4 would equal just the cube root of 2. Notation-wise, again, I'm not only going to really do it this one time here, because it's kind of a pain to write out, but you really should be writing the limit as x approaches 1 of the negative cube root of 2x minus 4 equals cube root of 2, like kind of rewrite the limit process when you're doing that. Those are finals. That's the only time I'm going to do that, but you really should, proper notation, be writing your final answer like that. I'm just going to write sequentially here, save myself a little space. For B, we have the limit as x approaches 3 pi over 4 for cosecant of x. So this would be cosecant of 3 pi over 4. If you remember your cosecant rules, great. If not, remember cosecant is 1 over sine. So 1 over sine of 3 pi over 4. That one you should definitely know. Sine and cosine would be straightforward enough to make sure you always know those. That's root 2 over 2. 1 over that is just simply the reciprocal. And then rationalize, it gets us 2 root 2 over 2, which is just simply root 2, because the 2's would cancel. So trig limits, just make sure you remember your unit circle information. And the rational functions here, let's not worry about factoring. First off, the top doesn't factor. The bottom, it doesn't either. But even if it did, let's never try and factor it first. Let's always substitute in and see what we get. And we get a negative 1/10 for that answer. So that's, again, it's all that's really happening for the vast majority of functions. It's at the interesting locations where something different happens. And that's what's called an indeterminate form. This is where typically with a rational function, though there are non-rational functions that create indeterminate forms, you're going to get 0 divided by 0. And there's a different process of doing this. Now, there are plenty of indeterminate forms that are also not 0 over 0. There's also infinity over infinity, infinity divided by 0, things like that are still indeterminate. We're going to only focus on 0 over 0 for right now, and we're only going to focus on 3 types of indeterminate forms. The dividing out, rationalizing, and combining fraction situations. There are plenty more involving trig, exponentials, logs, a whole bunch of other stuff. But for those, I typically prefer to use a method called L'Hopital's rule, which will involve the idea of a derivative, which we have not yet discussed. So that kind of situation, which we'll discuss in Unit 4 of this particular curriculum, we'll get into those other non-polynomial, non-rational function-based 0 over 0 scenarios or other indeterminate forms, infinity over infinity, stuff like that. We're going to focus on these 3 only. Now, for the rest of these problems, these are all 0 over 0, so we're going to go right into that idea. You will not know that just by a quick glance at it, whether it's part of my quiz or test, someone else's, AP test, anything else going on. You should never assume it's 0 over 0. You should always substitute in first and see what happens. And if we do that, for example, we'd have 2 squared minus 8 times 2 plus 12, or 4 minus 2 squared. We do get that to be 0 divided by 0. Okay, so you always should check that first, because if it's not 0 over 0, the rule we're going to discuss now, the techniques would just be useless, it'd be a waste of time. There's no point in factoring the quadratic expressions if it's not going to be 0 over 0. Just meaningless, waste of time there. So we factor, so the top would be x minus 2 and x minus 6. The bottom is a difference of 2 squares. It's not in the proper order, though. So when it's 4 minus x squared, we always pull a negative 1 out to make it x squared minus 4. So it's a negative 1, and then x minus 2x plus 2. You'll see that 2 terms will cancel. In fact, those 2 terms match the limit as x approaches 2 number right there. So if like limit as x approaches 5 was causing 0 over 0, you should expect an x minus 5 to cancel. Limit as x approaches negative 3 was causing an issue, then you would expect x plus 3 to cancel. But the idea is you need to factor, manipulate the expression in some way, and then once an expression cancels, now we can substitute back into the problem. So now we plug in the 2 minus 6 over negative 1 times 2 plus 2, we get negative 4 over negative 4, which is a positive 1. So our final answer, again, with our proper ran out notation, limit as x approaches 2 of the x squared minus 8x plus 12 over 4 minus x squared would simply equal 1. Graphically, this is the idea of a hole in the graph. So that's our dividing out technique. Just simple factoring. If you need to review quadratic factoring, find the appropriate videos for that from just really anywhere. Another technique is where we have radicals. Again, don't assume just because you see a radical in a rational function, it's automatically 0 over 0. Always substitute in, see what happens. 4 minus 4, square root of 4 plus 5 minus 3. This does, again, come out to be 0 over 0. Now, the technique we use here is we rationalize the expression. Now, it's very important. If the radical is up top and it gives us 0 over 0, we still rationalize the expression. We still multiply by those conjugate of that radical expression. Because it doesn't matter that the radical is in the top or the numerator. That's not really the issue. The issue is you're getting 0 over 0. So we manipulate it by multiplying top and bottom by the conjugate expression of that radical. Now, the reason why we're doing the conjugate is because when we have a minus b times a plus b, you just simply get a squared minus b squared. So that bottom would just be the first term squared, which is just x plus 5, minus the second term squared, which is 9. If you want to FOIL, you'll find the radical terms would cancel out anyway, so you kind of up to you there. But that's the whole purpose of the conjugate. Creates a squared minus b squared. Now the numerator, please do not FOIL that out. Leave that alone. Because on the bottom, in our denominator term there, you should find an x minus 4 shows up when we combine like terms. And again, nothing can be evaluated until something cancels from top and bottom. Now it has. Now we just simply have the square root of x plus 5 plus 3. Now we can go ahead and plug into that. So we would have 4 plus 5 plus 3, which is square root of 9 plus 3, which is 3 plus 3, which is 6. So we would say the limit as x approaches 4 of x minus 4 over square root of x plus 5 minus 3 is equal to 6. All right, so again, regardless of where the radical is, top or bottom, you need to go through the proper rationalization technique, multiplying by the conjugate, to allow us to cancel out the expression. Now do watch out. The numerator could have been, instead of an x minus 4, could have been a 2x minus 8, because it would have been 2 times x minus 4 to factor that to be able to cancel the x minus 4. So just always watch out for that. Again, the expression that's canceling should match whatever this number is right here. So it's approaching 4. There's got to be an x minus 4 canceling out somewhere. All right, so our last one that we don't really need the derivative techniques is the one where we've got complex fractions. So here you substitute a negative 2. You'd have negative 2 plus 2 over 1 over negative 2 plus 1/2, and that gives you, again, 0 over 0. So the idea, the only way we can deal with this is to get rid of the complex fraction. So the denominator fractions need a common denominator, multiply by 2, and multiply by x. We get 2 plus x over 2x. And again, if we have a fraction, we're dividing with fractions, all it is, top divided by bottom. So the top, x plus 2 divided by the bottom, 2 plus x over 2x. Well, that's really multiplying by the conjugates, 2x over 2 plus x. And I can put the x plus 2 over 1 there, and see the 2 plus x's cancel each other. I get just simply 2x. Couldn't substitute at any point until something actually cancels. And again, x is approaching negative 2. It makes logical sense that an x plus 2 expression cancels. So now we just do 2 times negative 2, which is negative 4. So our proper notation, limit as x approaches negative 2 of x plus 2 over 1 over x plus 1 over 2 is equal to negative 4. With our proper notation. All right, so that is that for our three different types of indeterminate formats. As I was saying earlier, there are plenty more, but those will be using derivative rules like L'Hopital's rule to be able to handle rather than these different, essentially these are all different dividing out techniques. We called this one with complex fractions, we called the other one rationalizing, all that kind of stuff, but it's still the same idea. We're still essentially dividing out an expression after we manipulate the equation in some manner. All right. In general, though, unlike what we just went through right there, you can never assume they're all indeterminate. So as I was saying, always substitute in first. If it's 0 over 0, use these techniques. If it's not, then your answer is whatever it is. If your answer is 5 divided by 7, then it's 5/7. If you get 0 divided by 6, that's 0. If you get 8 divided by 0, that's a does not exist scenario. It's more likely infinity or negative infinity based on what's really going on with the graph. And we'll talk about that kind of stuff because that's a vertical asymptote scenario in a later topic. All right. As always, appreciate everyone watching, and I'll see you next time.